Hi, good afternoon, everyone. My name is Qingyu Zhou, 30 years PhD student. I'm from Harbin Institute of Technology in China and supervised by Professor Ming Zhou. I'd like to introduce our work on abstractive sentence summarization by introducing the selective mechanism. And this work was done during my internship at Microsoft Research Asia. So now let's start from our motivation. As we all know, the sequence-to-sequence framework using the recurrent neural network-based encoder-decoder and the attention mechanism has achieved amazing progress in many tasks, such as neural machine translation, text summarization, question answering, dialogue generation, and so on and so forth. However, compared to the successful neural machine translation, in abstractive sentence summarization task, there is no explicit alignment relationship between the input sentence and the summary, except for the extracted common word. So the challenge here is not to infer the alignment, but to select the highlights while filtering out the secondary information. So let's recall how humans do sentence summarization. Normally, I think most of us will start from reading the sentence, and then we can grasp the main idea and select the important information by keeping it in mind or underlining some words. Finally, we can write the main idea of the sentence with our own language as concise as possible to get a good summary. So based on this idea, we introduce a simple but effective method called selective encoding. We explicitly model the select behavior of how humans do summarization. And we argue that a desired workflow for abstractive sentence summarization is encoding, selection, and decoding. So at first, our model reads the sentence to get an encoded sentence. Then we apply the the selective mechanism to select the highlights. And after selecting the important information from the encoded sentence, the decoder produces the output summary based on the selected information. This is an overview of our model. We incorporated the selective mechanism into the traditional sequence-to-sequence model with attention. Roughly, the model architecture reflects our designed workflow. First, encoding, and then selection, and finally, decoding. In our experiments, we use gated recurrent units, GRU, as the recurrent units. For the encoder, we use a bidirectional GRU to read the sentence words and produce a list of hidden vectors. These vectors are used as the first level representations. The decoder also uses a GRU to produce the output summaries using the attention mechanism. The selective mechanism in our model is implemented as a selective gate network. This selective gate network lies between the above encoder and decoder to construct the tailored representation for abstractive sentence summarization task. Specifically, the selective gate network controls how much information can pass through it from encoder to decoder. So now one remaining problem is how to define the importance of each word. Again, we designed this part based on our three-stage workflow: encoding, selection, and decoding. Since we have already encoded the input sentence, we can use it to construct the sentence meaning representation vector. In detail, the sentence meaning vector S is the concatenation of the first backward and the last forward hidden states. With the sentence meaning vector S, we can select the input words one by one with the selective gate. For each word xi, the selective gate takes two vectors as input, namely the hidden vector hi and the sentence meaning vector S. The MLP then produces a selective gate vector as gate I. We then multiply the hidden vector hi by the gate vector to get the tailored representation hi prime. Before the experiments, let's go through the related works. So one of the main challenges of training a generative sentence summarization system is the lack of training data. Banco used 8,000 article headline pairs to train their statistical machine translation system. And recently, Rush used English gigawords to construct a much larger article headline pair corpus. With the large-scale corpus, as training data, much progress has been made, and we pick 3 of them as our baseline models. The first one is Rush's work in 2015. They use a CNN encoder and a neural network language model decoder. They also tuned their ABS model using DOC 2003 dataset and get a better model, ABS+. The second baseline model is from Chopper's 2016 work. They keep the CNN encoder but replace the NLM decoder with recurrent neural networks. The third baseline model further extend the framework to a full recurrent neural network-based model. And they also combine some features in the encoder, such as post-tag and NER tag. Besides the baseline models, some other papers are also related to this task. In last year's ACL, 2 papers proposed different methods to solve the unknown or rare words problem using copy or pointing mechanism. So the first work, they jointly modeled the probability of the target vocabulary and source words to copy the words from source side to target side. And the second work used pointer networks to handle rare or unknown words. And our third baseline model also used this. So besides, sentence summarization task can also be done in an extractive way. So previous works model this as a sequence labeling task. Cheng and Lambda, they use pointer network to do this sequence labeling task. And before that, Filipova, they created a data set using heuristics on dependency trees. So we trained our model with the English gigaword data set and processed it with heuristic rules mentioned in our paper, which is also the same as our baseline methods. The final training set we used contained about 3.8 million sentence summarization summary pairs. And we conduct experiment on 3 test sets. The first one is the English gigaword test set. We use the test set provided by Professor Rush, and we also sample an internal test set since we found some invalid lines in this one. The second test set is the DOC 2004, and the last one is the MSR's Abstractive text compression test set. The first one, the English gigaword test set, is one of the most important test set in this task, since many previous work reported their model performance on it. We compare our model with 5 baseline models. The first 4 baseline results are copied from the corresponding papers. We also implemented one sequence-to-sequence with attention baseline model and trained it with the same data. Since there is no length limit for this test set, we report Rouge F1 scores on this test set. So on Rush's test set, our model outperforms all the baseline models significantly, given by the 95% confidence interval in the official Rouge script. And considering the fact that there are many invalid lines in this test set, so we further sample an internal test set and release it and report our model performance. The second one is the DOC 2004 test set. It is different from the previous one since the reference summaries are written by human. Another big difference is that in this setting of DOC task, the output summaries are capped to 75 bytes. So it forced the model to generate about 15 words to satisfy the minimum length requirement. Therefore, we report recall scores on this test set. On this test set, our model still performs better than other baseline models. So the last one test set is released in last year's EMLP, the Microsoft Research Abstractive text compression test set. It is created dedicatedly for the sentence summarization task by crowdsourcing. For each input sentence, the test set contains about 3 to 5 reference summaries. To note that this test set is very different from the first 2 since the average output summary length is much longer. Again, we reported full-length Rouge F1 scores. To the best of knowledge, this is the first work that report Rouge scores on this test set, and our model outperforms the baseline models by a large margin. So to verify how the selective mechanism influences the generation of summary, we used the method of Jiwei Li in last year's NAACL. So basically, the method measures how much each selective gate value contributes to the final decision, which can be approximated by the first derivatives. So we can get the gradient of each selective gate with respect to a given sentence output pair. However, the gradient is a high-dimensional vector. In our experiment, it is a 1024-dimensional vector, which is hard to visualize. We instead draw the Euclidean norm of this value. In this example, the Euclidean norm of each selective gate associated with each input words is visualized as a heat map. We can see that the important words like Europe, slammed, unacceptable, conditions, and France have larger impacts on the final outputs, which means they are relatively more important than other words. To summarize, in this work, we propose selective encoding for abstractive sentence summarization. The experimental results show on 3 different test sets shows the efficacy of the selective mechanism. And in the future, we are planning to apply this selective mechanism to other tasks, such as sentiment analysis. Thank you for being here today.
So thanks for the great talk. So my question is, it appears to me that the selective model seems to be a little bit similar to the attention model if the text generated is short. Do you have any study on comparing the attention value of those keywords like the summary-worthy contents compared with your selective model, like to say if they match together?
We haven't compared with that, with the attention mechanism.
Okay.
Since it's hard, the selective mechanism, it produces a vector. The attention mechanism, it produces a scalar, right? So we didn't compare with that.
So the selective model is applied to the every words in the input, right?
Yes.
So you can still use attention to say like which word in the input has been paid more attention to. Like
yeah, you can see that.
So
So we think that the attention mechanism, they also have implicitly modeled this, but according to our experiment, we think explicitly modeling selective behavior is better.
yeah, I can see your point that for longer text you can generate better probably because the attention model fails to capture the global like keywords, importance of words. So maybe that explains why.
Okay, thank you.
Thanks.
This is not really a question, but just a really naive confirmation. So you're basically saying that the usual way for us to do attention, where we compute a scalar for an attention weight, is not good, right? You say we should do this gate thing instead to basically do attention. Is that what you're trying to say in the paper?
Not actually.
Okay. So what is the point of the paper? Because your attention scheme, there's still an attention scheme in the paper,
yeah,
right? It's just that instead of a scalar, you have a gate which is a vector instead, right?
Yeah.
So what are you trying to say in the paper then? Like we shouldn't use our traditional attention scheme that we're doing, or?
So we still use the traditional attention mechanism.
So you have
right?
a scalar?
No, this not. That is still a scalar, right? Yes.
I thought it's a vector.
The select gate value is a vector.
Oh, could you show, maybe I missed it. Could you show where's the scalar part of the model? Yeah, so this is, you just basically do the Euclidean norm for your attention weights, right, which is a vector.
This is not the attention weight. This is the selective gate weight.
Okay, so can you point out in the architecture where is the scalar part of the attention? Yeah, I might have just missed it. Yeah.
This one?
Okay.
Yes.
So the MLP part produce a vector,
yes.
right? Which is the gate part, and then that is what you're gonna sum up. What do you do with that?
Multiply.
Oh, you just multiply with it. Yeah.
Multiply.
Okay. So there's no scalar anywhere, right?
Yeah, no scalar.
Yeah. So that's what I'm saying.
So upon this selective representation, there is still a attention mechanism.
Yes,
That
yes,
is a
correct,
scalar.
correct, correct. There is definitely an attention mechanism. Yeah.
This is different.
So you don't do any like usual weighted sum, basically. That's
No sum.
Yeah. So your point is don't do this weighted sum thing. Instead, do this style, right, where you actually basically attentioning to each of the units in your vector, essentially, when you have this sort of gate representation. If that makes sense.
We haven't tried
Okay.
that.
Don't worry about it. I'll
we
just
could-
talk to you offline. Yeah.
Thank you for your.
We have time for another question that I will ask, unless somebody else has a question. So I think with the previous questioner, I have a similar difficulty kind of conceptualizing the difference between attention and selection. So would you say, and one of the things I noticed is in your output is that with this mechanism, it seems that you really can produce more effective abstractive results where you get word substitutions that you might not anticipate from the data that you're training on, the summarization that you produce. So could you, and you're looking at me like I'm not making any sense. Okay. Well, could you just say a little bit more about what the selection mechanism, why it's a vector that you multiply, and what is it adding on top of the attention mechanism?
So I think mostly this selective mechanism, it is not adding anything. It is cutting something, right?
Okay.
It is a gate
So
scalar.
what it adds is a kind of pruning.
Yeah, pruning. Yeah.
Okay. And how does it achieve that? In the heat map, you're trying to help us visualize what it's doing.
Mm-hmm.
So it's basically, would you say that it's something like an importance value on your words? Because the words that get the selection weight in the way that you're visualizing it are the words that seem to be the most important.
Yeah. So I guess this is selected by the produced by the sentence meaning vector as right. So actually this for each word they will go into the same selective gate network with the sentence meaning vector, and it will produce a gate to mirror how important of these words, but it is more like a soft selection because it is a vector.